get into the construction of these Vey-Moore anima, but I want to remind you what the program is. So what? So we start with some K, some number theoretic field. So a local field, global field, finite field, something like this. And then we recognize some structure. So the first thing you get is a Galois category. Just corresponding to finite separable extensions of your field. But you also get these class groups. So sheaf of class groups. Defined differently in the different situations, but you have it in all cases. And this data together satisfies some axioms, which makes it into a class formation. This is completely canonical. You just recognize that you have this structure. And then there was a slightly non-canonical way to promote this. So promote. And it's slightly non-canonical, but it's the same Galois category. But now here you have a co-sheaf, a derived co-sheaf in degrees 0 and 1. So the sections of the co-sheaf are always living in homological degrees 0 and 1, but it is a co-sheaf in the full derived category, not just in some truncated version. And this is data which is saying that your H0 is fixed to be Z. And then the H1 will recover this, but the H1 is a co-sheaf, and to get the sheaf structure, you use transfer maps. That's how that works. Right, and this promotion is always possible, and we discussed in detail to what extent it's canonical in the given examples from number theory. Then we started to discuss that this gives canonically something like something that's equivalent to B of a Vey group, so some k pi 1 space, but this is the Vey groupoid. More canonically, if you don't choose a base point, you have a Vey groupoid that's basically the same data as this. We'll review it in a little while. And then there's another slightly non-canonical procedure of adding higher homotopy groups, which is what we're going to be discussing today, that gives you this Vey-Moore anima. And but before we get down to business on this, Maxime gently insisted that I should discuss a bit more some analogies in topology to maybe help orient it. So let me describe some class formations from topology. So here it's going to be kind of the opposite situation. We're sort of going to start with an object kind of like this, and then we'll get this data. So let's say X is, I don't know, so it's going to be a connected CW complex, and we only care about it up to homotopy equivalence. So really, at the moment at least, we only care about it up to homotopy equivalence. So say it's an anima. Then one can attempt to define a class formation. So certainly there's a Galois category. This is just the finite covering spaces. So that corresponds to the profinite group that's the profinite completion of the usual fundamental group. And, well, if you remember in class field theory, the sheaf of class groups it's kind of like, according to Artin reciprocity, it's a version of the abelianized fundamental group of your Galois cover. And in topology, we have the abelianized fundamental group is just given by the integral homology, so we could try the integral homology of our cover, the first integral homology of our cover, the abelianized fundamental group of our cover. And then that does have a system of transfer maps, so this does give a presheaf on Cx, presheaf of abelian groups on Cx. And then you could ask the question, so when is this a sheaf? And when is Cx H1 a class formation? And the answer is not very often. First of all, a remark. So far, all this data really only depends on pi 1. But we will see that okay. So now let me give at least one criterion for when this holds, and then you'll see that it's not very broadly satisfied, so it's not so interesting. And then I'll describe a modification of this story, which will have more interesting examples. So one answer. Suppose that the integral homology of y is 0 for all I bigger than 1, and then all finite covers of x. So if all finite covers have vanishing integral homology in degrees bigger than 1, then the answer is yes. And in fact, and this is the easiest way to see that you have a class formation in this case, is to see that you actually have a refined class formation. So Cx, and then if you take the chains on integral chains on any finite covering space, there's an obvious isomorphism with z in degree 0, giving you that data, and that's a refined class formation. And the axioms are completely obvious, because the only axiom really was that this should be a derived co-sheaf, but it's the integral chains, so it's. So this is
analogous to the case of finite fields, in some sense.
Yeah.
Because there, it's not exactly.
Yeah, you could take the circle for x, and this, you could say that this is analogous. So in particular, in this case, the transfer maps on H1 will give you a sheaf, and also these class field axioms will be satisfied. And it's just because this is obviously satisfies the axiomatics for a refined class formation. Okay, so that doesn't seem like it's very broadly satisfied, because this is kind of a one-dimensionality condition, whereas examples are more supposed to be two-dimensional. But there's an interesting aspect of the number theory situation is what we started with, basically, which is that the Artin map is not an isomorphism. So these class groups are not the abelianized Galois groups. They surject onto it, but they have a non-trivial connected kernel. And we can kind of mimic that situation here. So suppose, instead, so a less stringent hypothesis, so that hi, so yz equals 0 for all I bigger than 2 and all y. And suppose that h2y z is a finite free z module. Then I claim that there's no obstruction to writing down a refinement. A refinement of so something that refines this co-sheaf of integral chains with So that if you take the homology of this guy, this is 0 for I bigger than 1 now. So we got rid of the H2, but we brought it into the H1 instead. So the H1 now is going to be an extension of the usual H1 by the H2 tensor R mod Z. I guess I could just say the H2 with coefficients in R mod Z. So you can kind of bring you have an H2, which is some direct sum of z's in degree 2, but you can bring it down to a direct sum of R mod z's in degree 1. And then this H1, you have an H1 now, which is some topological abelian group, which surjects onto the usual H1 with some connected kernel. So it's more like the situation with class groups in number theory. So I'm kind of saying maybe that the connected component of the identity of the class group in the number field case can be interpreted as saying that secretly there's some H2 group. Okay, and then this will be there's still an alpha. This will be a refined class formation. And now there are lots of examples. So
here you claim that when you say no abstraction, there is no abstraction, and also the possibilities of doing it is essentially unique.
No, not essentially unique. Unique up to isomorphism, and then there's some choice involved.
So it's a non-contractible space of choices in some sense.
I'll make just a comment. So the remark is that this holds hypothesis. This relaxed hypothesis holds for X any closed 2 manifold, obviously, but also orientable or not. It doesn't matter. It can be non-orientable, or any X any compact 3 manifold with non-empty boundary.
But why not any two-dimensional so complex?
Probably that too.
I think it's homology.
Yeah, you're probably right. Yeah, you can't have torsion in the H2. Yeah. Okay, but these are the examples I'm particularly interested in. And then I claim...
You mean so that all its components are non-trivial boundary, not only that...
Yes, no, but I already assumed it was connected.
Okay.
Yeah. Right. So I claim that if you give X a Riemannian metric, then you get a canonical. I said there was a kind of potentially non-canonical way to make this refined chains, but I claim that if you choose a Riemannian metric, it's some geometric structure on your manifold, then you actually get a canonical choice. And the basic reason is that once you choose a Riemannian metric, then the chains with real coefficients gets a canonical splitting coming from the harmonic forms, coming from Hodge theory. Okay. So in this situation, which was supposed to be analogous to number theory, you do get something like a class group. And it is a class formation. And hopefully, Maxime, this also addresses the concern you had in the first lecture about the vanishing of HI for I bigger than 1. The essential reason is that there is secretly some H2, but it's kind of being put in the next degree down as some topological group. Yeah. So here's so for example, let's say, but this is still, I mean, it's not the only case where it's really analogous to the number field case. So note that these H1 groups can be infinite abelian groups. They could have positive rank. And then when you build these Vey groups, you're taking inverse limits of them along transition maps, and then you could have some, if the Betti number is growing, as it tends to do when you take finite covers, then you get some inverse limit of infinitely generated abelian groups, and you've kind of left the nice comforting world of locally compact groups. You've got some kind of pro-discrete group that's not necessarily locally compact. And that's not very analogous to the number theory case. So the only situation where you really have excellent analogy with number theory is that is in the case of finite fundamental group. So then get a Vey group. This would be a locally compact Hausdorff group. It'll just be an extension of this finite group by some torus like that, but in any case.
So how do you get it? From the class?
From the class formation, yeah.
No, why torus is if it's finite group, then the covers you could also get finite. You don't have hom to R mod Z will be finite.
Hom to R mod Z? Well, in this case at least, I mean, you have there's always going to be an R mod Z. This case I didn't think about in very much detail. It's possible, but I assume also there you can have some product of R mod Z's, depending on how many boundary components you have. All right. And then, well, as I'm going to explain, you can also build a Vey-Moore anima, potentially non-canonically, but I would kind of conjecture. So again, after a Riemannian structure, like the Vey-Moore. So we already know this is canonical, but also the Vey-Moore anima is canonical. So again, it's going to be a story where you have a bunch of obstructions that need to vanish, and you can prove they vanish, but they don't vanish canonically in principle. But I would guess that if you choose a Riemannian metric, then there should be a canonical way to vanish the obstructions, so to speak. So then let's call that Vey-Moore anima XWM.
By the way, so
Yes.
in your basic diagram, the passage from, so there was some promotion which to CXF alpha, but then there is a part in the classical theory of existence of L group where you need some compactness argument or countable tower.
That's right.
And so where is this step in your picture?
Well, it's right here. You still need those assumptions. You can always produce this, but if you want it to be of this form, then you need either a countability assumption or compactness assumption. But we'll get into that in more detail.
In general, when you don't have this,
it's going to be a bit of a mess, but there'll be different components. So, or it might even be empty. So then it's not a very nice construction. If you don't have those assumptions, this procedure, albeit canonical, doesn't yield a very nice output. So,
okay.
Yeah.
So you could have there in some tautological case an empty result because of some limb.
Yes, yeah, limb 2.
Limb 2 over some large cardinality aleph some. Okay, I understand this. Okay.
Yeah. But okay, in practice it doesn't happen in any case. We'll discuss it in a bit more detail after we have some topological preliminaries. So I would hope that this Vey-Moore anima is canonical, and also that, okay, so what role could this play? So we have the usual homotopy type, so the usual anima of X, but we also have the topological space X, or the condensed set, which we can view as condensed anima. And there's of course always a map from a manifold to its homotopy type. So from the condensed set underlying a manifold to the anima underlying the manifold. And this will factor through this Vey-Moore anima. So this is something that's going to sit in between the point set topology of X and the homotopy type. It's some kind of geometric refinement of the homotopy type. And I would expect, again, that if you choose a Riemannian metric, then also this map, this whole diagram here should be canonical, or there should be a canonical way to write down this whole diagram. So, note that here we're at the opposite end of the extreme from Mostow rigidity, right? When we have this finiteness here, then you don't expect that the homotopy type is enough to recover the geometry. But here you have a refinement of the homotopy type. I'm not saying that I expect this to be equivalent to the geometry necessarily, but at least it should come closer. You're seeing at least more of the geometry in this homotopy type.
So here is X is a 2-manifold, yes?
It could be two manifold or a 3-manifold with boundary.
Okay.
So complex is completely fine for your assumption. Finite is so complex.
I think from what I can tell, standing at the blackboard, you're correct. Yeah.
And homologies have torsion free and finite.
Yeah.
That's
Yeah.
it.
From what I can tell, you're correct. But then but the fact that a Riemannian metric induces canonical versions of this, I suppose that's true.
We replaced by manifold with boundary, often with high dimension.
Yeah, so then I already have 3-manifold with boundary, yeah.
So from 2-manifold, possibly with boundary, again, you...
2-manifold with boundary.
No,
Also, no.
2-manifold, close to manifold,
Yeah.
because you want the... Why should it be close to manifold?
I don't know. I just took this because that's what is analogous to the number theory situations in this analogy that I explained in the first lecture. So I'm not saying this is the best possible generality for the discussion. I'm just highlighting a certain situation.
No, I say it's finite. Two-dimensional so complex will be fine. Yeah.
Yeah, I'm sure you're right. But yeah, the question of what geometric structure means is maybe a little less clear in that generality. Okay, so maybe this geometric discussion clarifies a little bit what's going on in the arithmetic case. Maybe it doesn't. Probably depends on your background. But let's move on unless there are questions. Okay, so in the number theory examples, whoops. So the class groups are locally compact Hausdorff groups. And they're almost compact. And we're going to want to remember that structure. So already it's useful to remember the compactness for this step, as Ofer has already alluded to. But also here, to set up this obstruction theory for adding the higher homotopy groups, you kind of need to remember the topological structure. And that's part of the point. I said we were going to get a condensed anima at the end. So there's some kind of topological structure on the homotopy there. So really, yeah, we want just not just a sheaf of ordinary abelian groups, but we want a sheaf of condensed abelian groups. So we get and then it's not entirely obvious, but there is an abstract reason why in the examples that also this derived co-sheaf will also be a derived co-sheaf of condensed abelian groups. But maybe let me not go into that. Let's just use this as an excuse to do a little bit of a review of condensed stuff. So with a particular eye on the relationship with locally compact Hausdorff abelian groups or non-abelian groups, such as the Vey group. So the simplest form of the definition is the following. So a condensed set or group or abelian group or anima or derived abelian group, condensed object in D of Z, whatever category you like, is a functor x from a certain category to this target category that you're considering, such that, and then there's some axioms. But first, before I say the axioms, let me say what EXTR is. So EXTR is a certain very nice full subcategory of compact Hausdorff spaces. It's the extremely disconnected. Also known as projective. And it's also the retracts of stone check compactifications of discrete sets. They're just very big and inexplicit compact Hausdorff spaces. The only two important properties are that any compact Hausdorff space admits a continuous surjection from one of them, so you can cover anything by one of these inexplicit guys. And then maps from those, you can lift along surjections of compact Hausdorff spaces when you're mapping from one of these extremely disconnected guys. So it's basically allowing you to do things like projective resolutions at the level of topological spaces. Right, so the axioms are, the first axiom, or the zeroth axiom, is that X of the empty set is the terminal object. First axiom, X of a finite disjoint union of two such is also of the same form. And the third axiom is that, okay, this is not a small category. So you have to be a little careful talking about functors out of it. I mean, the simplest thing is to just fix some cutoff cardinal, some huge cutoff cardinal, bigger than anything you can imagine, but still small in the technical sense, and just look at these guys which are small. But then every time I talk about a compact Hausdorff space, I'd have to say a kappa small compact Hausdorff space, and I just want to save chalk. So, so X is a small colimit of representable presheaves. Representables. I'll just say representables. So let's ignore these set theoretic technicalities. Feel free to choose a kappa and cut off if you wish. So then it's basically just this. You send finite disjoint unions to finite products. Extremely simple definition. But so the intuition is that a topological space, basically all you ever need to know about a topological space in practice is how compact Hausdorff spaces map to it. Because most topological spaces you run into practice are compactly generated. For example, Banach spaces or locally compact Hausdorff spaces, whatever. But then if it's not, you don't even need to know how all compact Hausdorff spaces map in, because every one of these has a cover by one of these. So it's enough to know how these guys map in. And then at that level, the relations you have are extremely simple. Just this. Okay. So we have compact Hausdorff spaces, or in fact, locally compact Hausdorff spaces are a full subcategory of condensed sets by sending X to the functor, which associates S to X of S equals the set of continuous maps from S to X. And we're eventually going to be interested in doing things like homological algebra, but also homotopical algebra. But you should start with homological algebra. So we're going to be interested in the derived category of these things. So we want to be able to, so the key is that need to be able to calculate X groups.
So in the second axiom, X small colimit of representables, this makes sense when you go to sets. I'm not sure what you mean by.
But yeah.
In the second axiom 2.
For sets, yeah.
Yeah, so you could say for every, okay, it makes sense in Anima as well. Then say in this case, you look at any object in here and you look at Homs from that object to the values of this, and then you get a functor to Anima, and you want that to be small.
No, but the representable functor will give you something, a functor to set.
Right, or Anima. But then And then you look at Homs from a random object to that, and now that's an Anima. And then you ask that to be small.
But then colimit in the infinity set.
Yeah, yeah. Let's please, the technicalities are, I promise, not interesting. And they do work out, but it's just not fun. All right. So the key is that we need to be able to calculate X groups between locally compact abelian groups in this world here. So formally, Homs in IE. So Homs in the derived category of condensed abelian groups, which I just mean the thing where you take d of z here. That's my definition of this derived category from A to B I. But I'll just call this X to I. And in fact, we're going to use this a lot, but this was actually my design criterion when I was trying to settle on what definition to make. I wanted let me say the theorem that we proved. So for A, B in locally compact abelian groups, there's some obvious things. So one is that Hom from A to B is the usual continuous homomorphisms from A to B. But the second thing is that X1 from A to B is the usual X1, classifying extensions of locally compact abelian groups, meaning where the middle term in the extension is also a locally compact abelian group. And then the second thing is that XIAB equals 0 for I bigger than 1. So really it's as simple as possible. So in usual d of z, you obviously have xi vanishing for I bigger than 1, but it turns out in this context, even with locally compact Hausdorff groups, you have the exact same x vanishing. And I wanted this. I knew this was in the ideal world this would be true, and this definition, this condensed, is the only one for which I could prove this. So this was actually why that definition was chosen.
Are there extensions where the middle term is not locally?
No, I will. There are no extensions. I don't know about topological abelian groups. It probably depends what you mean. I don't know if it depends what you mean there, but in condensed
group and the quotient group is with the induced topology.
No, don't ask me about topological groups, but in condensed groups, it can't happen. Every extension. I'll make a remark about this. So. There's several remarks to make. So implicit here is the claim that the functor from locally compact abelian groups to condensed abelian groups is exact. So if you have an extension of locally compact abelian groups in the usual sense, then it's also an extension in condensed abelian groups. The only thing that you need to remark is, in fact, more generally, if you have an open surjection of locally compact Hausdorff spaces, then it's a surjection in condensed sets, epimorphism in condensed sets. That's the only non-obvious point here. And this is a general fact from point set topology that if you have an open surjection of locally compact Hausdorff spaces, then for any compact subset here, there exists a compact subset here whose image is that compact subset there. It's not entirely obvious, but it's true. But this is what implies that surjections in the usual sense in here go to surjections here. This is also true. So in fact, this is also true in the non-abelian case. So then this calculation 2 implies that if A to B to C is an extension of condensed groups, condensed abelian groups, with A and C locally compact Hausdorff, then B is also locally compact Hausdorff. But you can also prove this directly, and this is also true in the non-abelian case.
Non-abelian. So it looks like that A maybe is something more general, like with torsors.
Indeed. There's an even less abelian version and more analogous to this. And that's completely correct, that if you have a torsor for a locally compact Hausdorff group, where the base is a locally compact Hausdorff space, then the total space is also a locally compact Hausdorff space. That's what...
And in a torsor, you mean torsor in the condensed?
Correct. All right. So...
I think it should be possible probably to prove it just in topology, some other thing just in general topology.
Yeah, that argument is a general topology argument, yeah. That argument reduces to some standard general topology arguments, yeah.
After now, there's no number series, just topology.
Yeah, well...
Dimensional topology now.
Well, I mean, number theory is also all topology. There's this famous book of Vey called Basic Number Theory, where he basically just says, okay, number theory is just what you get when you combine field theory with, you just study locally compact Hausdorff fields. That's number theory. It's an interesting perspective. You can agree or disagree, but go read his book and you might just be convinced. All right. And also read his pithy comments at the beginning of the introduction. Okay, where was I? Oh yes, so that's one remark. The second remark, so there's implicitly I'm talking about this is an abelian group of Homs. This is an abelian group of X'd ones, and this is an abelian group of higher X'ds. But there's internal versions of everything. So there's the internal Hom, internal X'd, and the internal X'd I's. Basically, you just cross with an auxiliary extremely disconnected. And this theorem it holds for those as well. So the internal Hom from A to B is the condensed abelian group associated to the continuous homomorphisms from A to B with the compact open topology. So that a nice topology you put on such sets of homomorphism, compact open, that does describe the internal Hom and condensed abelian groups as well. And you do have the X'd I vanishing also in the internal sense. So the whole condensed group the whole condensed X'd I is also vanishing.
And the X1 underline will classify extensions parameterized by condensed.
Indeed, but I don't want to touch that. So yeah, that's correct. Yeah.
But you don't claim that you have a topology. Okay.
Yeah, I don't want to make any comparison to anything classical because, well, you could, but the classical thing probably was never defined, so why bother? Okay. Right, and there's another remark. So for if B is equal to R or R mod Z, or obviously any direct sum of these, then X'd I, also X'd1 underline A, B equals 0 for all A. I mean, for all locally compact abelian groups A. So in other words, these two guys behave like they're injective. Okay. Remark 4. So how do you prove such things? It's not because I'm interested in giving you the proof. It's that the key input is cohomology calculations. So the key idea is to reduce to cohomology calculations. And in the relevant cohomology calculations are the following. So if you have now a compact Hausdorff space, and then you have B, a discrete abelian group, then HIKB equals 0 for I. Oh, no, sorry. What am I saying? This is the usual sheaf cohomology. So this is cohomology taken in some condensed sense, and that's usual sheaf cohomology, which in this case agrees with Czech cohomology, but they're the same. K is K, yeah, X is K, yeah.
HI, what is the subscript?
Sheaf here and cond here. Yeah, so what does that mean? There's different ways of defining it, but let's say that it means let's say that it means X's from the free condensed abelian group on K to B.
Oh, that's cohomology in the condensed topos of set.
Yeah, that's also what you, yeah. Okay, so yeah, a key point is that, I should have mentioned this when I was saying the definition of condensed set, is that it's a topos, except for this business about the cardinality bounds. It's a topos, because the disjoint unions that we used are not just the disjoint unions of extremely disconnectigs are not just coproducts in the categorical sense, they're really disjoint unions. So they're, the fiber product is the initial object, and they're universal. You can pull back a disjoint union composition, you get a disjoint union decomposition. So that makes it a topos. And that's nice, especially when you're doing things like Postnikov towers and so on, which we will be. So that's one, and also for K in compact Hausdorff, and then B, say, equals R, then HI in the condensed sense, K with B coefficients, this is actually equal to 0 for I bigger than 0. And of course, H0 is just the continuous maps from K to B. So in the end, these abelian statements, these X statements, you can reduce them to these non-abelian statements, these cohomology calculations. Precise mechanism for how that happens is not relevant for us, but we will be also using such cohomology calculations, so I wanted to mention them.
You say discrete abelian group. Now
Yeah.
R is not discrete.
That's right, that's why it's a different statement.
Okay. Now you view R as a condensed sheaf and detect the, okay. So this is like the cohomology of the sheaf of continuous functions to R, which is a soft sheaf. Okay.
Yeah, but that's, yeah, so it's not obvious. So there it's also the same as usual sheaf cohomology, but that is, well, it's not an obvious statement. In any case, yeah. Okay, so let me see how we're doing on time. Right. So okay, so let me give some corollaries of these kinds of X calculations. So you could say this is derived Pontryagin duality, something we'll use quite a bit. So the first part is that, so define, let's say QLCA, subset condensed, full subcategory of condensed ab, which is those condensed abelian groups which are isomorphic to a quotient B mod A for some injection with both of these in locally compact abelian groups. Caution, an injective homomorphism need not have closed image.
Okay.
It could have a dense image. This could be Q with the discrete topology mapping to R with the usual Euclidean topology. But still there's a non-trivial co-kernel, and we include those objects. Then the first claim is that this is an abelian subcategory closed under extensions.
And when you say an abelian category, you mean also that the kernels and co-kernels are the same?
Yeah, abelian subcategory, a full abelian subcategory. Yeah. It's closed under kernels and co-kernels and extensions. So this follows formally from, especially for the only non-trivial point, you need the x2 vanishing. Once you have the x2 vanishing, then you can kind of formally see that this has to be the case. But anyway, this also makes it reasonable to define like unbounded derived category of locally compact abelian groups as a full subcategory of derived condensed abelian groups such that all the homology groups are in QLCA for all I. Then it's a nice triangulated category, stable category where you can take cofibers, fibers, whatever, and you'll stay inside.
Also, I think
DCLA. Yeah, this locally compact abelian. So it's in some sense the derived category of locally compact abelian groups, but it's the full subcategory, just where the homology groups are in this abelian envelope of locally compact abelian groups.
Also, for any exact category, like in the sense of Quillen, one can define the derived category in some. This was done so long ago, at least in the classic.
Yes, but you're probably familiar in scheme theory. It's often more convenient to, take a big ambient derived category and then impose conditions on homology than to think about derived categories of exact categories in the abstract. So we'll do the same thing here.
It should coincide.
Of course, it coincides. Yeah. So yes. Indeed, in this case, you can prove it coincides, but that's not relevant for us. We're just happy to have an ambient universe where all the calculations are correct. And it doesn't matter whether it agrees with one thing or another thing that might be defined a priori. Yeah.
DCLA?
DC? No, this is a parentheses. I'm sorry. This is open parentheses, close parentheses.
D of LCA.
LCA means locally compact abelian.
Because it's hard to pass.
I'm sorry.
C is the indistinguishable.
I see. Sorry. Yes. So if you define, so you can do a functor from D condab to D condab with an opposite by this to be the internal Hom. Well, I'm going to write R Hom just to emphasize that it's derived, but it's just the internal Hom from that guy to R mod Z. Then for all M in D LCA, this natural map, which you always have for obvious reasons, is an isomorphism. So it's a contravariant self-equivalence like this. And that also means that Homs from A to B is the same as Homs, also R Hom from B dual to A dual.
And also underlined?
Yeah, that I didn't check. I'm sure it's true. I didn't check. I'm sure it's true, but yeah. It doesn't follow formally, or maybe it does, I just didn't think carefully. But yeah, let me not claim that, and also let me not use it. It might follow formally.
because you can go in both directions once you know that in the ambient thing, in a large ambient thing, the dual is what.
Yeah, so I will make a remark that goes in a very similar direction, which probably also addresses that. So let's see. So, let me just do a quick example. So what if you take Q with the discrete topology, again, injecting into R with the ordinary topology. So then you have R mod Q discrete. Then what is the derived Pontryagin dual of R mod Q discrete? Well, it's actually just take the adels of Q mod R, and then shift it down by -1. Okay, just a calculation you can do. But then you can see also, I should add to this if M is A in degree 0 or A is in LCA, then M dual is the usual Pontryagin dual of A sitting in degree 0. So usual Pontryagin duality is a special case of this derived Pontryagin duality. But here this example shows that if you start with something in QLCA, it's still in degree 0, but the derived Pontryagin duality puts it not in degree 0, but somewhere else.
Sorry. Since this QLCA is completely elementary category, you could define without condensing.
Correct.
Just using locally compact group.
Correct. Yeah, it's formal. You make formal quotients of locally compact abelian groups. Yeah. Right. Okay. So let me make another remark. So if G is any condensed group, then this automatically promotes to, you can make a G equivariant version. So if this is a full subcategory of G conda ab, you just have a derived condensed abelian group with G action where on homology groups you just ask that the underlying object lives in QLCA, and just for purely formal reasons, topos-theoretic, this kind of derived Pontryagin duality, the G structure gets carried along for the ride, and you get all of these things with G structure as well. So if G is acting on everything, then I can also do Pontryagin duality like this. And this, I think, is similar to what Ofer was asking about.
I mean, you mean a abelian group or?
No, it's a group of operators.
A condensed group, just any, then you have LCA. Okay, this means the derived of LC.
So I look in the derived category of condensed objects over BG, condensed objects with a G action, and I just put the condition on homology that when you forget the G action, you live in this category here. Then this Pontryagin duality just promotes to that level for formal reasons.
Okay, so here you are not claiming that there is actually a strict action on each term of the complex,
right,
just in some derived sense.
That's correct.
But then it will be real. Okay, it doesn't.
It's irrelevant whether it can be concretely realized or not. So this version with the G action is actually quite useful of this derived Pontryagin duality. We'll see some examples. So let me also give another corollary, which is that if AI, I and I is a filtered inverse system, of now compact Hausdorff abelian groups, then the higher derived limits, I said maybe J, yeah, are equal to 0. So for J bigger than 0, there's no higher derived limits of compact Hausdorff groups. Also in the condensed object is also equal to 0. This is you just take the Pontryagin dual system of discrete groups, then the filtered colimit, there's no derived functors for filtered colimits, and So that lives in degree 0, but it's also just a discrete group. And when you do derived Pontryagin duality again, as I said, it brings you back to the compact group living in degree 0, which is just the inverse system of these guys. And that actually just proves that these higher derived limits are vanishing.
And what is the condensed version of this statement?
I just put an underline here.
Okay, so you take the derived in the condensed topos, which...
Yeah. Yeah.
Okay, then this is an...
I mean, the S-valued points of this guy will just be the higher derived, the Rj of inverse limit of continuous maps from S to AI.
This for S dot restrict.
Exactly, for S extremely disconnected, yeah. So it's also a concrete statement that not only do you have lim vanishing for the system of compact groups, but for any extremely disconnected thing, and you take continuous homomorphisms to that, which no longer carries a compact Hausdorff topology. But nonetheless, the lim i's will still vanish.
There is a standard complex that computes it, so once it's exact, you can lift by the compactness.
Exactly. Yes, yeah, exactly. That's one way to look at it. Yeah. Yep. Okay. Right. So, and let me make a remark that there's also the non-abelian version. The full subcategory of condensed groupoids, or let me just say condensed anima, spanned by the BG for G, a compact Hausdorff group, is closed under filtered inverse limits. So in the case where the groups are abelian, that's actually a consequence of the thing I said before, but it can be formulated in the non-abelian case, and it's also true in the non-abelian case.
This is like some vanishing of non-abelian H2?
Exactly.
So okay, so you have some gerb. Okay, so
you can prove it. I'm sure you can prove it very quickly, but let's not do it in front of everybody. Okay, so I just want to do one last thing before the break, which is so that's the, so suppose G is now a profinite group. This is relevant. And then let's say A and B are just discrete abelian groups with G action. So this is this kind of classical situation you study in Galois cohomology. When you're doing Galois cohomology, for example, you have a profinite group of operators and you have discrete groups with continuous G action. So they're just the union of the H fixed points for H open subgroups. Now, so there's two different things you can mean by the X groups. So this can either be the usual Xi in the abelian category. So these guys form an abelian category. It's also just sheaves on the Galois category associated to G. And you have the usual Xi in that abelian category as calculated by injective resolutions. But on the other hand, you have this the Xi in the condensed sense from A to B. So this is just so Homs in this DG cond ab from A to B shifted by I. And there's a natural map and it's an isomorphism. So the standard cohomology that is group cohomology with discrete coefficients for profinite groups, or X groups even, is the same as the thing you just natively get from doing everything derived condensed. The proof is not difficult, so it just reduces to case where B is continuous functions from G to some injective abelian group. By injective resolutions of B, you can reduce to that case. And then you just need to see that these guys vanish in positive degrees for this. But this is also the derived, there's no higher derived functors for continuous maps from G to this because G is profinite in the previous cohomology calculation. And then that tells you that this is the co-free object, and then it's just, and then you reduce to the fact that an injective abelian group doesn't have any X's either. So it's a very, very short argument giving this. Let us take a 5-minute break. Everyone, I was realizing during the break that there was just a couple more things about cohomology I wanted to mention before moving on. So remember when we were talking about cohomology of compact Hausdorff spaces with discrete coefficients? I just want to make a remark. I'll just say it orally that if you look at the condensed structure on that, it is discrete. So the cohomology of a compact Hausdorff space with discrete coefficients is discrete. This actually follows from the plane statement because the S-valued points is just the cohomology on S cross K. And if you calculate what that is, you see that it commutes with filtered inverse limits in S, which is one manifestation of the discreteness. But okay, so the condensed structure is trivial in that case. And also, so I'll make a remark. So that's a remark on cohomology. So for K compact Hausdorff, HI, K, say Z, or any discrete abelian group, is discrete. And 2, so you can, so let's say G is a Lie group, a real Lie group. So in particular, the cohomology of G as an underlying condensed set, will be the usual cohomology of G with integer coefficients. This extends to not this statement that it's discrete necessarily, but the comparison with sheaf cohomology extends to the locally compact Hausdorff space for obvious reasons. So if G is a Lie group, then I want to say that the cohomology of BG with discrete coefficients is the same as the cohomology of the usual Anima, or the classifying space from algebraic topology. So there's a standard way of talking about the cohomology of BG in algebraic topology, and if you just take G as a condensed group and look at cohomology of BG with discrete coefficients, you are just getting that usual topological cohomology, of course. Right. And but if you do it with R coefficients, then you're getting the if you do it with R coefficients, let's say it's a countable union of compact sets, just to be safe. Then this is the usual continuous cohomology with R coefficients, as occurs in Van Est's theorem, for example. And that just follows it follows from what I explained about compact Hausdorff spaces. Well, again, it's easy to pass to locally compact Hausdorff spaces by just exhausting by compact subsets. Assume it's countably exhausted. Then you just immediately see that this cohomology, you can resolve BG by the standard bar construction of G. And then because there's no higher cohomology on G or G cross G or G cross G, that tells you that this cohomology is just calculated by the complex of continuous cochains in that case.
Yeah, but since G is the disjoint union of the connected components, it's even you don't need accountability even.
I recognize that you're correct about that. Thank you. Yes. Yeah. Okay. Right. Okay. And another thing about back to the profinite group case. So G profinite. We have X, I, AR equals 0 and X. Also, the other way around, RA. So I view R as having the trivial G action. And this is for all locally compact abelian groups A with continuous G action. Oh, 0. Yeah, both ways by derived Pontryagin duality. So this way you can argue similarly to this. Here you use that this guy is a retract of, so this obviously embeds into continuous functions, but it's actually a retract by the Haar measure, so you can integrate on the Haar measure. So then it's enough to prove X vanishing for this, and then that reduces to X vanishing without the G action from A to R, which we already had in our X calculations for locally compact abelian groups. But then this one actually follows by derived Pontryagin duality.
But then the R will be the circle instead.
What? No, the Pontryagin dual of R is R.
R goes to R.
Yeah. So that's, yeah. So we will actually use that you can kind of ignore R factors when you're calculating X groups, as long as, if you're calculating like an X3, for example, you don't have to worry so much about the R's. Okay.
You mean for I bigger than?
I bigger than 0, yeah. Sorry. Right. Okay, so now we come to the main theme, which is taking objects that are like BG and then adding higher homotopy groups to them. Let me just make a small definition so that G be a locally compact Hausdorff group. So we'll say G is almost compact if there exists a closed normal subgroup K sub G such that, so the first condition is that K is compact, and the second condition is that this G mod K, which is a group, I said this is a normal subgroup, this is isomorphic to either a 0, a Z under addition, I should say 1, but okay. It happens to be abelian and isomorphic to it's either trivial or it's Z under addition or it's R under addition. Okay, this is simply...
Only once, yeah? Not 2Z, yeah?
What?
G mod K can
Z square is allowed?
Yeah, I only allow 1 Z. And it's... there's two reasons, which are probably the same reason. One is that this is the only case of a free abelian group that's also free as a non-abelian group. And the other reason is that the cohomological dimension of this is 1. Okay.
And you can probably split it in all cases.
Okay, yes, indeed. So in all cases, that's a semi-direct product. In this case, it's even a direct product automatically. That's not entirely obvious, but it's true. All right. So this is just an attempt to axiomatize what Vey groups look like in practice, because Vey groups are pretty much compact, but they have this little extra quotient that's either Z, R, or either Z or R. And it's barely more work to handle these two cases than this case, especially because of facts like this. So in the number field case, you will have this, or the Archimedean case will have this. In non-Archimedean cases, you'll have this for your Vey groups. Because of facts like this, it's like this case is not that much harder than this case. Ironically, this case is slightly more troubling, the non-Archimedean case, but then it's easier for other reasons. Okay, what I'm trying to get at is, for the purposes of the rest of the lecture, and maybe also most of tomorrow's lecture, I'm going to assume we're in this case for simplicity, even though in the number theoretic examples, you're in one of these cases instead. It's not that much more trouble to handle those cases, but it just introduces a couple of technical wrinkles that I don't want to have to discuss in these lectures. So, of course, in the number field case, you have class formations, which put you in this case. You just pass to the norm 1 subgroups of the Adel class groups, and that's fine. So in that sense, it's not such a big deal. So that's my excuse for, from now on, only working with compact groups. So for simplicity, from now on, G compact in this lecture. So we're interested in condensed anima X such that, so the first thing is that, again, it should be pi 0 should be trivial and the pi 1 should be this compact Hausdorff group G. So let me put those two statements together and say that the less than or equal to 1 truncation is just BG. And then pi I of X is compact Hausdorff abelian group for all I bigger than, well, I guess, yeah. And it's the same as you have on pi 1, but it's abelian for I bigger than 1. Ooh, I forgot to make another remark about condensed things. So here's an important fact about the condensed topos. The terminal object behaves like a point. So if you have a terminal object in a general topos, it doesn't behave at all, in general, it doesn't behave at all like a point. For example, sheaves on a topological space, X, the terminal object behaves like a topological space X that's not a point. So formally, what does this mean? So the functor, like this functor, let's say from condensed anima to anima, it preserves everything. Limits, that's obvious, but it also preserves co-limits, arbitrary co-limits. It preserves Postnikov truncations, preserves anything you like.
So is it in the topos sense, it's a point that is the final object defines a point of the topos? A point in
That's correct. It's a point of the topos. Yeah, yeah. Yeah. So any torsor over point is trivial, or any higher, whatever. It's any surjection to the terminal object admits a section. So there's no possible global twists over the point. So in particular, the reason I'm mentioning it is it's justified to forget the base point here. Any two points, i.e. maps from the terminal object to X, are actually homotopic. So by the usual argument, the homotopy groups are well defined up to conjugation. Okay. That's not true in a general topos, so I thought I should bring it up.
But this topos could have many other points?
Excuse me?
Is it the only point of this topos?
Okay, then it depends on your technical foundations, I think. If you choose a cutoff cardinal, there will be other points, but they're. So for example, basically, if you have an extremely disconnected profinite set and a point there, then taking the stock. For every extremely disconnected profinite set, you will get a sheaf in the usual sense on that thing just by restriction. And taking a stock, that will also be a point of the topos. So, yeah.
And when you consider like homotopy sheaves or things that you will get things which are isomorphic, well, I don't know, something.
Well, as I said, the pi I x in this case are well defined up to isomorphism as condensed groups. And once you assume that pi 0 of x is the base point, then all the higher homotopy groups, pi 1, pi 2, are well defined up to isomorphism. So the conditions I wrote make sense.
Sorry, but we closed in that language you said condensed anima and just anima.
Right. What is?
We have condensed anima and just anima.
Yeah.
I don't understand it, sorry.
So anima just means infinity category of homotopy types.
Okay.
An object in the infinity category of homotopy types.
Oh, okay.
Yeah, and a condensed anima is a functor from extremely disconnected to, yeah. All right. So yeah, so we'll be interested in condensed anima satisfying these conditions. We could call them condensed anima of compact type. I don't know. So these kind of have nice properties. So for such an X, so we can extend what we know about the cohomology. We can just propagate it up the Postnikov tower by sort of standard arguments. And we get that if A is a discrete abelian group, First claim, which is nice, so the functor, so for all I bigger than or equal to 0, the functor HIX blank from condensed abelian groups with G action, or from a category equivalent to this once you fix a base point. Don't come at me about that at the moment. Two condensed abelian groups preserves filtered colimits. The second thing is that if A is discrete with G action, then HIXA is also discrete. For all I. Third, and maybe I'll also say that if, 3, so if X is a filtered inverse limit of Xi's, then, so filtered, then, the pi1 of X is the inverse limit of the pi1 of Xi's, the pi2 of X is the inverse limit of the pi2 Xi, etc. So the homotopy groups are naive in a filtered inverse limit of such things. And also the cohomology with discrete coefficients is naive, or is the colimit. So, oh no, J. Let's switch to J. Yeah. So on the level of cohomology, you get a filtered colimit.
These claims stay true if G is almost compact, or?
So far, yes. Yeah.
But they don't if I slightly.
The next one I say is not exactly going to be true, but it's so close that it hardly matters. But okay. So also HI of X with R coefficients, 0 for I bigger than 0, and H0 of X with R coefficients is R. Right. So all of these things are simple to prove. Maybe I should make another statement. Maybe I'll just say it out loud. You can always write, so it's a well-known fact, consequence of the Peter-Weil theorem, that every compact Hausdorff group is an inverse limit of compact Lie groups. This extends to such objects. So every such X can be written as a filtered inverse limit of a special kind of such X, the one where all the homotopy groups are compact Lie groups. Not just compact Hausdorff groups, but so the pi1 is a compact Lie group, the pi2 is a abelian compact Lie group, so product, torus cross a finite abelian group, and so on for all the higher homotopy groups. You can always arrange your X to be an inverse limit of such things. And then if you take this statement, you see that the cohomology of your x with discrete coefficients is just filtered colimit of some usual cohomology of, well, objects slightly more general than Lie groups because they can have higher homotopy groups that are also Lie groups. But yeah, we won't use that remark, but it's just maybe psychologically comforting to know that you can reduce more or less formally to the case of Lie groups.
So here in topology, pi 1 acts on pi higher pi.
Yes.
Okay, here, what happens?
Also pi 1 acts.
Pi 1 acts
Yeah.
on the higher pi. So of
Yeah.
course you can do this, because if you choose a base point of x of like x star, you can choose a base point that, okay, you could, no, but I'm worried still about those points, bad points of the topos, like from a point in total, so you get some other point to which the usual point is a retract, and so a priori there you could think that when you define the pi I, when you value the stock on such a thing, then you get.
No, there's simply nothing to worry about. So your x is covered by point, and yeah, it's.
X is covered by. Okay, because it is connect. All right, okay.
So you can always test things on pullback to point, and there's really nothing to worry about. I appreciate, yeah, I mean, I appreciate that one can, it takes reflection to see that, but all right. So let's make a corollary. So the most important, because of this derived Pontryagin duality, the most important coefficient system is not the ones I've so far discussed. The most important coefficient system is R mod Z. But R mod Z just sits in an obvious short exact sequence with Z, which is discrete, and R, which I just talked about over there. So you can calculate, well, the upshot is that this is R mod Z. If I equals 0, it is the continuous homomorphisms, obviously, from G to R mod Z. So the Pontryagin dual to the abelianization of G, if I is equal to 1. And then for all higher, it's just a cohomology with Z coefficients with a shift. So because the R cohomology vanishes. Okay. So now let me make a remark. So suppose A is now a general locally compact abelian group, and you want to know the cohomology of X with coefficients in A, then you can actually reduce to this case. Then, so let me write it like this. So R gamma of X with coefficients in A is the same thing as R hom in D of Cond ab from the Pontryagin dual of A to this R mod Z cohomology. Thank you very much, indeed. Thank you. Yes. Yeah. Okay. So now, if you want to know the cohomology with any locally compact Hausdorff coefficients, it's kind of determined by things we discussed, R homs. Note that this lies in this, in particular, this corollary shows that you lie in the full subcategory I denoted DLCA. This object here. And then you just do an R hom calculation from the Pontryagin dual. That's convenient. But there's something that needs to be taken into account, which is the possibility of twisted coefficient systems. So far I've only discussed cohomology with constant coefficients. So where G is not acting. So what if...
But here in part 1 you already said something about cohomology. Like
Excuse me?
here in this.
Yeah? Oh, I did say, yeah, that's right. There's one case where I did make a completely general statement, yes. Okay, what if G acts non-trivially on A? Then it's a bit more complicated. Let me make a simplifying assumption. So eventually we're going to try to understand how to build such x's. Starting just from G, we want to know how to build a nice x. We want to know a good way to add higher homotopy groups. So we're going to be adding compact Hausdorff higher homotopy groups. Then the relevant thing, like the pi1 action on the higher pi i's, it'll be G acting on a compact Hausdorff abelian group. So let's put ourselves in that setting. So the remark that I want to make is that, so note, the automorphism group of a compact Hausdorff abelian group is totally disconnected. So that means that this, it factors through the connected component of the identity. And this is a profinite group here. So all of your coefficient systems come from a profinite group acting on a compact Hausdorff group. But by Pontryagin duality, that's also the same data as, as a profinite group acting on a discrete group, which is exactly this classical situation that we were talking about before. Okay. So how to leverage this? So now suppose given x, x as above, as before. So let me make a definition. So let me write, don't take this too seriously, it's just notation, but connected component of the identity of x. Let me define that to be, so let me fix the base point, at least in BG, just for convenience. So then I know what the connected component of the identity is, and I know what this is. And I just take this to be the fiber product there. Then the data of x equipped with its map to BG, which is giving the one truncation in our example, is equivalent to the data of the same thing but with a connected component, but this being equivariant with respect to this profinite group. So I should say it like this map. So the datum of this guy is the same as the datum of this guy equipped with this action here, not necessarily preserving the base point. And then the datum of this x can be equivalently read in terms of the data of this x circle.
Claim that G over G connected acts on VG.
Yes. Not fixing the base point.
But how does it act on X?
Just because it not just acts on BG, but it acts on BG over, it acts on BG circ over as an object in the slice category.
Okay, with the identity action on BG.
Yeah.
Okay, because you can view it as a kind of a bundle of, okay.
Yeah, indeed. So this is a variant of the usual trick from algebraic topology of passing to the universal cover, but I still have a pi1, but the pi1 is connected, so it kind of feels like it should be a pi2 instead. But anyway, so this is something like saying that topology on X is like equivariant topology for the fundamental group acting on the universal cover of X. It's a version of that. Okay.
So, and the outcome of this discussion is that somehow G0 does not affect.
G0 doesn't affect.
Doesn't affect the category of local systems on X. Like.
So let me say what the outcome is. Yeah. So the consequence of this is that if A is a compact Hausdorff abelian group with a continuous action of G, then similarly to this, but with non-trivial coefficient systems. So then this action lets us view it as a coefficient system on X, and the cohomology is given by R Homs. Now in this D for the profinite group, equivariant derived category for the profinite group of the Pontryagin dual of A, now in the cohomology of X circle. Okay, it's literally just this with some equivariance via this trick here.
And if it is not compact Hausdorff but more general with a G action, then it's also true.
Then it's also true if you went all the way to point here. So then you would have to contend with how the connected component is possibly acting, and you wouldn't be able to reduce to a profinite group. But yeah, the same story. If you did a modification of this idea where you did point mapping to BG instead, and instead of G mod G circ you had G, then that would still work, but it's a benefit here that you're able to reduce to the case of a profinite group acting.
No, I'm asking about A.
A? What's A?
A is not here is compact
Yes.
Hausdorff, but if it's only locally compact.
And that's what I'm answering. Yeah. The only thing that changes, that what you don't have is this claim that the action descends to an action of G mod G circ. But you still have an action of G, and then you could do the same thing. So there's an okay. So R hom G, A dual, R gamma, X twiddle, yeah, R mod Z, where X twiddle is X cross BG point. So this version is now true for all A, but it's not as useful for us because it's harder to control R homs over G when G is a general thing than when it's profinite. And the profinite case brings us back into the realm of the discussion we had last time of class formations and so on.
It was used that all local systems with coefficients in compact Hausdorff abelian groups on F0 are trivial.
Right. Right. Okay, so this means that the Postnikov tower of X is classified by. So how does it work in general? You have like the nth truncation, and above it you have the n plus first truncation. And the fiber here is some Eilenberg-MacLane space in degree n plus 1 with a compact abelian group coefficients. But first of all, that compact abelian group is acquiring an action of the fundamental group. But second of all, the action on the induced monodromy action on the fiber might not be preserving the base point. So it's not just determined by the action on the group A that you get, but there's an additional invariant called the K invariant, which classifies the gerb that you're seeing here. And then that's, so it's actually a twisted bundle thing, but okay. So you have, so it's better if you pass to this thing. And then you have this situation here, and here you have an actual K invariant, which goes to, kappa, and this is K as an Eilenberg-MacLane space. So K A, now n plus 2. So now this is what's going to be pi n plus 1 of X as a G mod G circ equivariant thing, and this kappa should be G mod G circ equivariant. So in other words, it's classified by a map from A dual to R gamma X naught R mod Z shifted by n plus 2 in this equivariant derived category for this profinite group. Truncation? Excuse me. Yes, thank you. Yeah, thank you. Yeah. Yeah. So if you have just the n truncation and you want to build the n plus first truncation, you have to choose what compact abelian group you want to add as your next homotopy group. You have to choose what action of this profinite group you're going to put on it. And then you have to choose this k invariant, which equivalently is a map like this. Okay. So now let me make a definition. So let G be a compact Hausdorff group. So a more anima for G is an X mapping to BG such that, so first of all, we want that this is the first truncation. And second of all, we want that so let's say hi is equal to 0 for all I bigger than 1. So remember what the goal was. The goal was to add higher homotopy groups to this BG in order to make the cohomology as simple as possible. We just saw that the cohomology in general is controlled just by this guy. So we want to make this guy as simple as possible. So we want to make that vanish in degrees bigger than 1.
In the condensed sense.
Well, it doesn't matter because I already said that the R mod Z cohomology in high enough degrees is just a shift of the Z cohomology and that the Z cohomology is discrete. So this condition in the condensed sense and in the ordinary sense are equivalent conditions. Yeah. Now you can play this game, I should say, yes, you can play this game, so some obstruction theory. So, by the way, the class, so analog of some work of Dustin Smith in classical topology on equivariant Moore spaces. So it's the problem of trying to build a CW complex with a given pi1, and then where the homology of the universal cover just lives in a single degree, and the action of pi1 on that abelian group is specified in it beforehand. That's the problem of equivariant Moore spaces. And this fellow, wait, was that the right name? Excuse me. I have the paper here just to make sure I don't mess it up. Dustin Smith, yes, Dustin Smith. This fellow Dustin Smith analyzed that, and if you use basically the same idea in the condensed setting, you get what I'm about to what I'm about to say. So this gives a theorem that in the situation as above, suppose that H2 of B of the connected component with coefficients in R mod Z is equal to 0, and that X I and G mod G0 from M to CG, something I'll define in a second, is equal to 0 for all I bigger than 2. Then there exists Moore anima. And it's unique up to isomorphism. So I just have to define for you what CG is. And what M is. So I have to tell you what CG and M is. Maybe I should say what M is here. So for all I greater than 2, and for all M discrete abelian group with G action, with G mod G0 action. Where CG is, so it's the thing that we're going to want to end up being this cohomology here.
And the uniqueness after isomorphism is also in some higher sense?
No, it's just, unfortunately, I do not know whether the space is simply connected. I just know that it's connected. So you take the R mod Z cohomology of this, but then you only retain the cohomological degree 0 and 1 parts of it.
Sorry,
Yes.
what's the word -1?
Well, that's because I put it underneath, so it's homological.
Okay.
Yeah. Right. So, again, I should say that this kind of, well, maybe I could give an idea. I could remind you about how Sarah's thesis goes, if you want to get an idea of how this works. Should I do it? Yeah, well, it's fun, right? Okay, so just to get, so analogy is building S2 from KZ2. So for those of you who are not algebraic topologists, or maybe you don't know this quite as well, but let's pretend that you don't know S2, but you're really trying to find a space. You know Eilenberg-MacLane spaces. You're a good algebraist. You know how to make classifying spaces and stuff. And you don't know any geometry, so you don't know that there's this round object called the sphere. But you want to try to build something that has homology just in degree 2, and the homology is the integers. But all you know is Eilenberg-MacLane spaces, which have homotopy in a given degree, not homology in a given degree. So how do you do it? Well, you take the closest you can get so far, which is KZ2, and then you calculate its homology, and you see that it looks like the desired answer up until degree 4. So the H1 is 0, H2 is Z, H3 is 0, but H4 is Z. And so you don't want that to be true. So you want to get rid of that homology in degree 4. The way you get rid of that homology in degree 4 is you make a map. So the homology in degree 4, there's dual cohomology in degree 4. So you make a map classifying that. You know that these Eilenberg-MacLane spaces classify cohomology. So you make a map like this, which represents the dual to the homology you calculated in degree 4. And then you view this as classifying the next step in the, so then you have an x3, this is x2, it's good up to degree 2. Then you make your x3 by just taking the homotopy fiber. So that now this is something where the fiber is a kz3. So you've added a pi3 here, which is equal to the integers. And then you go and you calculate the homology of that guy using the Serre spectral sequence. And then you find, okay, it was just like this one, it's good up to degree 2, but it's also in degree 3 good, and it's also in degree 4 good. You fixed it all the way up to degree 4, kind of by construction. But then the nice thing is, in degree 5, it's also good. It's also 0 in degree 5. And then the next thing is something in degree 6, which, if I'm not mistaken, is a Z mod 2. And it's important that it was not just good in degree 4, but also in degree 5, so that when you map to the next non-trivial guy, it's actually classifying. Oh, no, 5. Yeah, no, 4. And not just 3. Sorry, no, it's only good up to degree 4. But okay, in principle, yeah. Okay, so it's good up to degree 4, and not just degree 3, so that when you map to this guy, you're actually classifying the next stage in the Postnikov tower, x4, which has a k z mod 2 4 here. So you get a little bit better every time, and you keep on going, and after a while you can't actually physically compute what the relevant homology groups are, but you can still abstractly prove that the process can be continued, and that you can build up the Postnikov tower of S2, and then in the inverse limit you get S2.
Okay, so self-proving, for example, that the homotopy groups are finite by analyzing this kind of...
Yes, right. Yeah, so you can understand. Serre developed this mod C theory, right? That's beside the point. So, but there's what's relevant here. Say you have a group acting on the whole situation, like in Justin Smith's paper, or like in our situation, but condensed. Then this part here becomes problematic. So if you look at chains on your xn with integer coefficients as a G object, you have no right to find a map which realizes the top part of it. So you want to map to the top part. That's what's going on here. You're just picking out the top, something giving the top homology. Now, of course, if you just have a chain complex of abelian groups, you know it splits into the direct sum of its homology in some way or another. So of course you can map to the top part. But in general, you can only map to, canonically, you can only map to the bottom part when you have a chain complex of abelian groups. But you need to be able to map to a top part. And when you're doing things equivariantly, there's obstructions to splitting the chain complex and thereby defining what the map is to the top part, which is exactly what you need to get this guy. But in our case, we're requiring that the homology we're making the homology be 0 in a range. So this thing that we're building we have at the nth stage, it's got something in the top part and then a bunch of zeros, and then it's got this little bit at the bottom part, which is exactly coming from the cohomology in degrees 0 and 1, which is wrapped up in this single object, giving the degree 0 and 1 part. So there's just an obstruction to splitting that G equivariant guy, and the obstruction exactly lives in groups like this for certain values of I that you have to analyze. But the relevant I gets bigger and bigger as you go up the Postnikov tower, and then it's exactly something like this that obstructs being able to split this complex and thereby map out to the top part.
And where is the first assumption used? H2BG.
Yeah. I said that it was important that when you go here, you don't just have the right homology in degree 3, but also in degree 4. And so if you want to just get started at the very first step, you start with BG circ, and you want to repair the homology. You're going to be in terrible trouble if the homology is already, or the I'm doing now, instead of homology, I'm doing cohomology with R mod Z coefficients. It's equivalent by Pontryagin duality. You're going to be in trouble if this is non-zero, because then you'll try to fix that, but you'll fix that by a map to an Eilenberg-MacLane space in degree 2, and then whoops, you just changed the fundamental group, but you didn't add any higher homotopy groups. So if the cohomology is bad in degree 2, then at the first step, you'll be making a map like this.
Okay, and then this means that you add a fiber which has a fundamental group, and you don't want to do it.
Right.
Okay.
Yeah.
And again, in the classical setup, you said that it involves splitting a chain complex, the homologically bottom part. But this splitting is not unique. You can have in the derived category, and this gives some choice or not?
Yes.
In the classical.
Well, but the two choices are homotopic, but they're not canonically homotopic. I mean, there's choice. I mean. The two choices will be homotopic, but I mean, when you have a G acting, all of a sudden it's quite important, because then there might not even be a choice. But the important thing here is that you shouldn't try to, you have to bundle the bottom part together, the bottom two things together, and not try to make an obstruction with this guy and then make an obstruction with this guy. It's only when you take the 0 and 1 degree information together that you actually have this x vanishing in practice. And that's, so this is not living in degree 0, right? This is an x to something that lives in 2 degrees. But now this ties in exactly to the kind of information that you get from refined class formation. So theorem. So suppose CF alpha is a condensed refined class formation. I just mean that this cosheaf takes values in derived condensed abelian groups such that, okay, now I'm going to have some axioms. So the first axiom is that, so we have A as usual is the sheaf you get by passing the transfer maps in the H1. Now it's an important thing that I was reminded of during the break, that this procedure of going from a cosheaf to a sheaf is not duality. It's a covariant operation. It's something different that's maybe not entirely familiar, but it's a way to go from going from sheaves to cosheaves, which is covariant instead of contravariant. I guess it's like Verdier duality in a sense, but in the profinite group case. Right, so for all U and C connected, A of U is almost compact. And the kernel of the map from A of U to the global sections of A is compact. And then, for all open subgroups of finite index, let's say H in AU, there exists a V mapping to U such that the image of A of V inside A of U is smaller than H. Okay, so this corresponds to the existence theorem in class field theory. So it's the thing that says that not only, so we had from the abstract formalism, we have that the abelianized Galois group is some quotient of the class group. And it's the quotient by the intersection of all the norm subgroups. But you want to know also that you have enough abelian extensions, and that statement is that any finite index open subgroup, finite index, in case we're in the Z case, finite index open subgroup is actually contains a norm subgroup. Then you'll know there is some abelian extension corresponding to it. So that's exactly what this is requiring. And then I also have some technical things. So either A of U is compact for all U, or A of U is Z-type for all U, and the kernel of this is profinite. I don't want to have to deal with other connected things in the Z-type, or A of U is R-type for all U. Okay, so
AU1.
That means that, so it's Z-type, so you have this quotient which is isomorphic to Z, and I denote this by the kernel. And I want in general it would only be you could only assume it's compact, but I'm going to assume it's actually profinite. So again, in the non-Archimedean, it turns out in practice that you're in these situations. And then I also have to assume that if Z-type, then Okay, this is just technical. I need to assume that the so-called, so to speak, inertia group has cohomological dimension 1, so with torsion coefficients. Again, it's satisfied in practice. I wish I could get rid of the assumption, but I can't. Huh? Yeah, okay. It'll come in the statement. So those are my hypotheses. Then, so the first statement is that the Vey groupoid is BW, or this is now a Vey group. So it is the Vey group in the number theoretic examples. And the second thing is that the hypotheses in previous theorem are satisfied. So you get a Vey Moore anima, a Vey anima, or a Moore anima. Mapping to BW. And then the third is that it's closely related to the definition, but it's not exactly the definition. Is that for all, you see, so for all y to x finite étale, so corresponding to just a finite index open subgroup of W, say y is connected, then R gamma y R mod z equals 0. Oh, sorry, hi for I bigger than 1. And let me add, the refined class formation is recovered. And this is maybe the most important point, as excuse me, I have to put it somewhere. Let's put it here. Okay, the refined class formation is recovered as, so C is, the finite étale site of X. F is, you want to say that kind of the chains, so F of Y for Y to X finite étale. But what you do is you take the cohomology with R mod Z coefficients, and then you take the derived Pontryagin dual. And then alpha is induced by the map from Y to point. Okay, so this is in this situation, when you have a Moore anima arising from this set of data, that's what I'll call a Vey Moore anima. And the point is, I view this as trying to point to the fact that when you have a class formation, there should be a geometric explanation for why the class formation axioms are satisfied, akin to the one I gave at the beginning of this lecture in the topological setting, that you have when you have a CW complex where the homology of each finite cover is only in H0 and H1. That gives an easy explanation for why you have a class formation. And somehow we were trying to go backwards. We're trying to say in number theory we have a class formation. It should be explained by the fact that you're just taking the homology of finite covers, where that homology just happens to live in only 2 degrees, 0 and 1. We made it so that that was true. Alpha, there was the data in a refined class formation that you have to say that the H0 is specified to be isomorphic to Z. Yes, okay. And so I take this operation, if I apply it to when Y is a point, then I get the Pontryagin dual of R mod Z, which is Z. So by functoriality, I get a map from this to Z, and that's my alpha.
And this should be an iso.
It's an iso in degree 0, yeah. When Y is connected. Okay, I went a little bit over, I'm sorry for that.
I'm sorry, I forgot. So last time, when there was this refined class formation, we defined Weil group corresponding to it?
We spoke a few words quickly at the end. So the idea was that each term in the refined class formation is something that some object in the derived category where the h0 is z and the h1 is something. So all such things correspond to gerbs. But there was G acting, so it's a gerb over BG, and then you just take the inverse limit of all of those things. You have to make sure that to make sure you're still getting something of the form BW, you need to know that some higher derived limits vanish. But I explained under compactness assumptions that that's going to be true. Yeah.
Under compactness, so there either exists and it is a groupoid, and it is
It's a connected groupoid.
connected.
Yeah.
And presumably one can use some higher limb 2 or something which is not 0 over some large thing that, I mean, without compactness 2. And
that's right.
so if it's countable, you know that this vanishes. So, but you don't know the uniqueness, maybe, or you do.
No, you do. Well, no, you know the uniqueness. You do know the uniqueness because you can prove that the transition maps, homomorphisms on the Vey groups are actually surjective. So in the countable case, it's not just the pi 0 is not just non-empty. It's also a point. So,
Okay.
yeah, because you know a priori that you have surjective transition maps. So in the countable case, there's nothing to worry about. I mean, but there is something to worry about that the inverse limit you get, the pi 1 would not be a locally compact abelian group anymore. Like I was discussing, a locally compact group anymore. Like it could be an inverse, usually an inverse limit of locally compact groups is not going to be locally compact, but only if you have some compactness assumption on the fibers, then. So the same assumption that gives you higher limb vanishing without countability of hypothesis is also just important on abstract grounds so that the limit object is still locally compact. So you might as well just throw it in and forget about the countability assumptions.
Which holds in the number theory case anyway, so
yes,
it's not.
That's true, but it's not really relevant to use it. Any other questions? Okay. All right, thanks everyone.